Welcome back, everyone. In this video, we're given a region D, so it's a nice triangle in the plane, and that's going to be the domain for the function z equals xy, and there's going to be some surface xy, right, defined over this domain. Now, maybe we know how to graph it, maybe we don't, but we're not so concerned here about what the actual graph is as much as what the volume under that surface is. And even without knowing how to graph it, we can absolutely compute that. We're going to do it by computing a double integral. And there's going to be two actual approaches I'm going to show in this video. One is by describing this D as what I call a type X region, or what Stewart calls a type 1 region, and then also as a type Y region, or as Stewart calls it, a type 2 region. So we're going to do it twice. So I'm going to start with doing a type X region. So how do we write D as a type X region? So we do that by first describing explicitly all the values X can take on in this region. And you can see pretty easily X can take any value between 0 and 3. All right, now we want to know about the Y value. So the way I do this is by just choosing some point, representative point somewhere, and drawing the vertical line. This shows me all the different Y values I can take on. And you see pretty quickly I can get down as low as 0. So my Y coordinate is going to always go down to 0. But it is bounded from above by whatever this line is. Okay, well, let's see. I need to figure out what this line is. It's a straight line, so it's got a slope and an intercept. Ooh, I can see the intercept is 0, so I just need the slope. Let's see. It rises 2 and it runs 3. So this has got to be y equals 2 over 3 times x. And so the y coordinate is always going to be less than or equal to this line, y equals 2/3 x. And so the y is bounded here by 2/3 x. Okay, well, once I have that, I can now compute the volume by computing the double integral over the region D of the function, which in this case is x times y. And by Fubini's theorem, I can write this as the integral x goes from 0 to 3, followed by the integral y going from 0 to 2/3 x. xy, and now the y is on the inside, so we do a dy first, followed by a dx. All right, well, let's compute this inner integral first. So an antiderivative with respect to y is going to treat x as a constant. So I can actually pull that out, right? In fact, I can pull all these x's out and just put those together. So I'll actually write it in this way. Is that fair? Well, no, let's hold off on the dx because that's right. We still have a 2/3 x up here we got to worry about. So we'll pull the x out. When I anti-differentiate y with respect to y, I get y squared over 2. So I'm going to get y squared over 2, and then I'm going to evaluate that between 0 and 2/3 x. So we'll write it like this, 2 over 3 times x. All right, and then we'll toss this dx over here. I mean, it wouldn't have hurt to put it on the other side, but it's just going to feel a little weird. Okay, so let's see. When we evaluate y squared at 2/3 x, we're going to get something. When we evaluate it at 0, it'll be 0. So I only have to worry about it at 2/3 x. So let's see. When I square it, I get 4/9 x squared. Divide that by 2, and I guess I'll get 2/9 x squared. And then there's one more x. So that'll be 2/9 x cubed. And x is going from 0 to 3. And then we go times dx. All right, so one more integration here. When I anti-differentiate x cubed, I get x to the 4th over 4. So we'll have that, and then we evaluate between 0 and 3. At 0, of course, it's going to go away again, so we just worry about it at 3. 3 to the 4th, that is, 81? 81 over 9 is 9. 9 times 2 is 18. 18 over 4 is 9 halves. Okay, so we compute the volume in one way, and we get 9 halves. Why don't we check it the other way now? So to check it the other way, we're going to set this up as a type Y region. So in this, as a type Y region, we're going to first specify the values you can get for Y. explicitly. So we'd say, okay, well, the y values range anywhere between 0 and 2. Now, I'm going to draw a vertical, or rather a horizontal line for a particular y. So I say I have some particular y, and I actually just get these points. It starts on this line, and it ends at 3. So my x value is always going to be able to go up to 3, but it's going to have to be bigger than this line. And I'm going to want to write this in terms of x. So I can do that by multiplying by 3/2. And so I'll have x is equal to 3/2 y. So my x coordinate on this purple line is always at least as big as 3/2 y. So that'll be the range, or the domain rather, for my x coordinate. And so now I can again write my volume. Okay, it's still a double integral over d xy dA. But now again, by Fubini, I can break it up as an iterated integral, only now I start with the y's. So y goes from 0 to 2, and then x goes from 3/2 y to 3. Nope, and now we do dx first, and then dy. All right. Now you'll notice when I switch the order of integration, they're no longer the same bounds. All right, and that's going to happen when we don't just have rectangles, but more complicated regions. Okay, let's see. Well, this y is a constant, so I can pull that out. And then what's left over? I have an x. Anti-differentiate x, I get x squared over 2. And I need to evaluate that between 3/2 y and 3. Okay, so let's see. The integral from 0 to 2, we have a y. When we evaluate it at 3, we're going to get 3 squared, which is 9 over 2. That's 9/2. Minus, now we evaluate this at x at 3/2 y, which is, let's see, when we square it, we're going to get 9/4 y squared. Divided by 2 will be 9/8 y squared. Okay, and then we have a dy. All right, well, let's see. We probably should distribute this y. And we'll have 9/2 y minus 9/8 y cubed. Remember our parentheses, times dy. Okay, so anti-differentiate y, we get y squared over 2 times 9/2 will be 9y squared over 4. Okay, minus, now we anti-differentiate y cubed, we get y to the 4th over 4, and times 9/8, that'll be 9y to the 4th over 4 times 8, which is 32. And then we'll evaluate this between 0 and 2. Okay, let's see. Well, at 0, it's clear, right? The y's are all going to become 0. So we'll only have to worry about this at y equals 2. So first thing we're going to get 2 squared is 4. Over 4 is 1. So we just get a 9. Minus, now let's see, 2 to the 4th, that's 16. 16 over 32 is a half. So this will be 9 over 2. And 9 minus 9/2 is 9/2. Hey, check it out. We got the exact same value either way. Who would have thought Fubini's theorem would actually work? Craziness.